Hello everybody, it is time for us to look at the 6-5 worksheet, which is all about the properties of special parallelograms. This first problem here is kind of a doozy because it is a proof and it's a pretty long proof. So it says write a proof of theorem 6-16, which is the one that says if you have a rhombus, then the diagonals of the rhombus are perpendicular bisectors of each other. So I went ahead and wrote a paragraph proof for this one, and I'll kind of explain it to you. We know that by definition, all of the sides of a rhombus are congruent, and that includes the opposite sides, or the sides adjacent to each other. So what I did is I wrote that first. I said WX is congruent to XY, which is congruent to YZ, which is congruent to ZW, by the definition of a rhombus. By the definition of a rhombus. And I also, based on that information, know that X and Z are equally distant from W and Y. So X is the same distance from W as it is from Y. Z is the same distance from W as it is from Y. And I know the same thing about W and Y. W is the same distance from X and Z. Y is the same distance from X as it is from Z. So I'm going to write X and Z are equidistant from W and Y, and W and Y are equidistant from X and Z. W and Y are equidistant from X and Z. So therefore, we have the perpendicular bisector theorem that tells us if there is a point that is equidistant from two endpoints, that point is on the perpendicular bisector. So for instance, since X is equidistant from these endpoints, it is on the perpendicular bisector of XY. So therefore, by the perpendicular bisector theorem, I know that X and Z are on the perpendicular bisector of WY. X and Z are on the perpendicular bisector of WY, and the opposite. W and Y are on the perpendicular bisector of XZ. So both of those are true. And since that is true, since X and Z are both on the perpendicular bisector, that means that the line XZ that you create by connecting those is the perpendicular bisector of WY. So therefore, and this reason is kind of weird. It's by the definition of a line, since we can draw a line between any 2 points. Therefore, by the definition of a line, that means that XZ is the perpendicular bisector of WY, and WY is the perpendicular bisector of XZ, and therefore we have proven our theorem. Number 14, figure ABCD is a rhombus. What is Malcolm's error? So since ABCD is a rhombus, AB is congruent to CD, we know that. Since the diagonals of a rhombus bisect one another, then Malcolm says AE is congruent to BE, is congruent to CE, is congruent to DE. So by side, 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 all triangle ABE is congruent to triangle CDE. And when we're looking at this, the problem is that the diagonals of a rhombus bisect each other, but they're not necessarily congruent. So they're bisecting each other, so they're divided into two congruent pieces, but those pieces are not all four congruent to one another. So the diagonals of a rhombus bisect each other, but they are not necessarily congruent. Not necessarily congruent. So you can say two things. You can say AE is congruent to CE and BE is congruent to DE. They're just not all four necessarily congruent. Coming up here, the area of this rectangle is 115.5. What is the perimeter of the rectangle? Explain your work. Let's see how we can do this one here. So we know that PQ is 4 inches, which means, of course, that we know that this side as well, from the center to the edge, is also 4 inches, which means that the entire height of the rectangle is 8 inches. So if the area of the rectangle is 115.5 and the width of the rectangle is 8, I can do 115.5 divided by 8 and get 14.43. So I know that the entire length of the rectangle is 14.43. I also know that when we are making the diagonals, they intersect at the center. So I know that I can divide this right in half and say that each of these is 7.21 approximately by rounding. It's like 7.215-ish or something like that. So then, if we want to find the perimeter of triangle XYZ, because that's where we're going here, that's the perimeter of half the shape, almost like what we call the semi-perimeter of the shape, just like this. So I need to find the length of the diagonal. Luckily, it's pretty easy because I can just use the side lengths that I have in the Pythagorean theorem. So I can say 8 squared plus 14.4344 squared equals c squared. That's 64 plus 208.4 is equal to c squared, which gives me, when I solve this, I add them together, that's 272.4 squared equals c squared. And then when I take the square root of both sides, oops, it's not squared on that. I apologize, there's no squared there. 4 equals c squared. So that when I take the square root of both sides, I'm going to get roughly 16.5 equals c. That's my hypotenuse. So in this triangle, I have 8 plus the hypotenuse of 16.5 plus the side length of 14.43 or 44. I've rounded a little bit differently throughout this whole problem. And so that is going to give me 38.93 for the perimeter of that triangle. Down here, we've got to find each angle measure in the rhombus. So we see some angle measures 7x minus 6 and 4x minus 3. These angles are complementary. They add to 90 because I know that this angle right here will be 4x minus 3. So those two angles together will add to 90. So I can say 7x minus 6 plus 4x minus 3 equals 90. Combine like terms, 11x minus 9 equals 90. Solve. X equals 9. So then we're finding measurements here. We're finding the measure of angle ACD, which is another 7x minus 6 angle right here. So if I do 7 times 9, I get 63. 63 minus 6 is 57 degrees. So that's 57 degrees. The measure of angle ABC. So ABC is a double angle here. It's 2 of these 4x minus 3s. So 4 times 9 is 36. 36 minus 3 is 33. So this angle here, ABE, is 33, which means the measure of angle ABC is 66 degrees. And then the measure of angle BEA, that's one of our central angles here, so that's 90 degrees in a rhombus. Down here, for exercises 24 through 27, find the length and angle measures for rectangle GHJK. So we know that this is a 7 by 10 rectangle with a 52 degree angle. So when we find the measure of angle GHK, GHK is going to be supplementary because it is going to be the same as angle HGL. So this angle right here is 38. 90 minus 52 is 38. So angle HLG is also 38 degrees. So that's 38. The measure of angle HLJ is going to be right here. So to find that one, I would say, well, I know that each of these top angles is 52 because that rectangle is symmetrical this way. We have 52 here, 52 here. So we can do 180 minus 104, both those angles. And we find that HLJ is 76 degrees. Then we want to find GJ. That is the diagonal of this rectangle. So we're going to use the Pythagorean theorem. So we're going to say 7 squared plus 10 squared equals c squared. That's 49 plus 100 equals c squared. 149 equals c squared. And when we take the square root of both sides, we get approximately 12.2 equals c. So that's the diagonal GJ, that's 12.2. And then HL is half of that. Since the diagonals of a rectangle are congruent to one another, HL is half of 12.2, or 6.1. All right, let's keep going. If ABCD is a square, what is GC? All right, if ABCD is a square, then all of the diagonals will be congruent to one another, and they're all bisected. So, as it looks like BF is 16, and we're looking for GC right here. So we know that FG is 10 because, again, that's symmetrical and bisected. But from F to C will be 16. So we just do 16 minus the 10 we already know, and we find out that GC is 6 units. Number 32, Jordan wants a collapsible puppy pen that gives his puppy at least 35 square feet of area and at least 10 feet of diagonal length. Should Jordan buy the pen shown and explain? So if he wants the pen to have at least 35 square feet of area, then he's probably going to want to put this pen at its square setting so that it is a 6 by 6 square rather than any kind of rhombus. Because a square that is 6 units on all sides is going to be 36 square feet. 36 square feet. And since that is the only sort of setup of this puppy pen that is at least 35 square feet, then we also need to see if this pen setting up this way has 10 feet of diagonal length. So we just need to find the length of the diagonal of this square. So we just do 6 squared plus 6 squared equals c squared. That's 36. So 72 equals c squared. Take the square root of 72, and we're going to get roughly 8.48 equals c. So the diagonal of this pen is 8.48 feet, which is unfortunately not at least 10 feet of diagonal length. So no, because if she sets up the pen with at least 35 square feet, if she sets up the pen with at least 35 square feet, the diagonal will be less than 10. The diagonal will be less than 10. And I have to correct this because this looks like it says feet, and that's making me upset. Feet. There we go. Then the diagonal will be less than 10. So it's not a big enough pen for that puppy. 35, which statements are true about all rectangles? The diagonals of all rectangles bisect each other because all rectangles are parallelograms. The adjacent sides are perpendicular because rectangles have 90-degree angles. The diagonals are not perpendicular. They're perpendicular in a square and a rhombus, but not necessarily a rectangle. And the consecutive angles are supplementary. Since they are all 90, they all add up to 180. 36, which expression gives the measure of angle DBC? So the measure of angle DBC is this one right here. Put a dot on. That's the one we're looking for. So since these are congruent triangles, which have a vertex angle of 3x, then we can find the measure of angle B by doing the total, 180, minus the 3x that we have, that we know, and then taking that total and dividing it in half because we want half of that amount. So that is going to give us C. And then 33 actually doesn't have a question associated with it. I forgot to put the question in. So we're just going to ignore 33 right there, not do it. All right, and that is everything for the 6-5 worksheet. Let me know if you've got any questions, and have a